All right, so today we're going to learn inscribed angles. So inscribed angles, of course, just like we learn anything new, that we need to have a definition first, so we know what we are talking about. Now, inscribed angle means the vertex is on the circle. Now, there is something most people probably don't know, uh, that when in math, when we mean a circle, we just mean this, that. That is called a circle, not the interior. Just this, we call it, this is a circumference. So the vertex on the circle has to be on, this means will either be here or here, but it has to be on those lines, on those, this kind of circular lines. And so that's one thing. It has to be on the vertex on the circle. And second of all, it have two sides. The two sides has to be the core of the circle. Now, this angle is something we called inscribed angle. So something inscribed on the circle, and that's why we have that. And of course, we could have this cut the arc. We learned arc before. So this circle kind of cut this this arc. Now we could have a circle which this is called a minor circle because this is less than 180. The other one, the other side, this one is called the major circle. Now, when we're talking about inscribed angle, is basically what this two arc is point to. So we're actually about this, we cut this arc. And it could have an inscribed angle that it could be something like this. So therefore, this angle then facing the arc, which is we call the major arc. So that's basically we get two kinds of that. And actually, if we want to be really, really accurate, we could say there is a one more type of inscribed angle is that it is 90 degrees. So the angle, of course, either be less than 90 degrees or greater than 90 degrees. Okay, now for this one, we do have a theorem about that. The theorem says, we can see that theorem 3-1-4 said the measure of inscribed angle. So when we say the measure, we're talking about how big that inscribed angle is. Now there's two ways to measure it. One is by degree, another one is by radian. So here we're pretty much just using degree. And this theorem says that if you have inscribed angle and there is a called intercepted arc. So this arc here is intercepted by the two sides of the angle. So that's called intercepted arc. And we see that the degree, the measure of that is half of the degree measure of the intercepted arc. Okay. So now, of course, we want to know how do we prove that? And we're actually going to break down into three kinds. You can see that one kind, case one is that one of the arc actually it went through the center. And later on, we'll see that once we can prove this case, then the other two become relatively easy. So this is our key steps. First one, we're going to draw a radius from O to here. And we're going to call that the measure of ABC. We're talking about this measure, which we're trying to find. and we call them X. So give a name to it. And one thing we know that is this angle is going to be also the same measure as this angle. So the measure for angle A is also, we write like this, measure angle A is also equal to X. Now, why is that? Why those two angles are congruent? Hello, Grayson? So,
Sorry, I forgot I was on.
okay, we call this angle angle B or ABC, this angle
Mhm.
X, give a name. And by some property that, or by some reason, we know this angle is going to be congruent to angle B. That means the measure angle A is also X. And what is the reason?
Sorry, which angle's congruent
Angle A is congruent to angle B.
to angle A and B?
They are congruent, right? It's always red.
Oh, um, because it makes a triangle.
Well, mixed triangle doesn't mean that they have to be congruent. There's a reason that they are congruent.
Because A and B are both they both it meets.
Okay. Look at what kind of triangle is that?
Um, it's a
So we look at triangle,
um, it's an
we look
acute
at the
triangle.
triangle. This is our triangle.
Hmm.
What kind of triangle is that?
It's an acute triangle.
No, it's not acute. Actually, this is obtuse
Oh,
triangle, but it's a special kind of triangle.
isosceles.
Isosceles. Okay, what's a property for isosceles triangle?
Two of the sides are equal.
And what else?
It adds up to 180 degrees.
Oh, that's for any triangle. There is special property for isosceles triangle. The definition of isosceles triangle is that there's two sides are congruent, but
Mhm.
also there's a property for the isosceles triangle. Do you remember?
I can't remember.
Well, the two base angles are congruent. Good.
Oh yeah.
Okay. So that's why for the measure of angle A is X. Well, if that's the case, then we know that the angle AOC, so we're talking about this angle now. We're talking about color. This angle. This angle is 2x. Why is that? So we know measure of AOC is 2x. Why is that?
What's X supposed to be again?
X is angle B. So basically, first of all, we define X, the angle ABC, which is basically angle B, we let it equal to X. So that's basically a definition. We
Oh,
define
okay.
x equal to that. And we know that because AOB is isosceles triangle, so therefore angle A, the measure of angle A is also x. And because of that, then the measure of AOC, which is one I put on angle here, that is twice of x. So why is that? Very important properties for a triangle. Okay. Do you remember?
Um, is it uh, is it the exterior angle theorem?
Yes. Exterior angle theorem. What does that say?
Um, that the exterior angle of the triangle is the sum of the two inside.
Yep, very good. So that's why we got this. Good job. Okay. Well, now we know this is a 2x. And this is the center angle. So therefore, the corresponding arc has to be 2x. Well, we just said that angle B is x. So therefore, angle B, measure of angle B is actually half of the measure of the intercepted arc, which is AC. Good.
Yes.
So that's very important. We actually proved that for this case, is that this angle is half the angle measure of this, or the half of this angle. Measure this angle and also its corresponding intercepted arc. Okay, so now that's kind of our starting point. Okay, and we're going to show how do we do case 2 and case 3 later on in our classroom exercise. Okay, now here, just give an example. We have this. Well, we want to find x and y. Well, where's x? X is here. This is the line here. This is x. Well, x, the corresponding arc, the intercept arc is 40 degrees. So therefore, x is 20 degrees, half of that. So pretty straightforward. And we want to find y. Y is this part. And the corresponding inscribed angle is here, which is 50 degrees. Now we know 50 degrees will be half of the arc from here to here. So it's half of the measure of arc PR. But the PR is two parts. One is 40 degrees and the other one just y. So we set the equation like that. Therefore, we can times 2 on both sides. We got 100, and this is a 40 plus y. So therefore, y is 100 minus 40 equals 60. So pretty straightforward um, algebra. All right, so that's how we got that. Okay, good. All right. Now we're going to, based on our theorem, 3-4-1, we're going to have, I think we have three corollaries. Now, corollary just a simple theorem based on another theorem. So this actually is based on our theorem 3-4-1. So the first one said, if two inscribed angles intersect the same arc, the angle are congruent. So in this case, we get angle 1 and angle 2. Well, they both intercept the same arc. So therefore, let's call this one A and B. So therefore, the measure of angle 1 is going to be half the measure of AB. And of course, measure of 2 is also half the arc of AB. So this side is the same. Therefore, uh, the measure angle 1 is equal to measure angle 2. Now, in algebra, we actually have basically two parallel languages. One is use equation. When we say measure, we use equation. Or we use uh, congruency. So congruency is the terminology if we look at as shapes. Um, this is another terminology when we look in them as a number. So with numbers, we use equal sign. As geometric shapes, we use congruency, this sign. So when we see this versus this, we pretty much talk about the same thing, but with different emphasis. This one, we emphasize that they have the same measure. And this one, we emphasize on the shape. We say those two have the same shape. It's basically, if you put two angles together, they will on top of each other. Okay? Now you can see that why it's called corollary, because it's pretty straightforward based on the uh, theorem. Okay, corollary one, we said an angle inscribed in a semicircle is a right angle. Well, we see here. We see that uh, this is angle X. Now, angle X, the arc is from here to here. Now, we know this arc basically 180. And based on the theorem, this angle will be half of that, which basically is 90 degrees. So you can see that pretty straightforward. Basically, it's applying the theorem to this special case. Good. Now, this one has a practical application, like how do you draw a right angle? Well, if you have a compass, you can always draw a circle, and you can find this diameter because you know that there's a center. You have to get the center before you can draw the circle. Once you have a center, just draw a line pass through the center. That's diameter, and then you're going to draw a triangle, inscribed triangle. It doesn't matter where you are. If you do here, that's 90 degrees. Now, if you do it here, also we got 90 degrees. And if you do here, also 90 degrees, no matter where you are, the triangle you make is a right triangle. Good? Yeah. Grayson, we good? Okay. So we're going to look at the next corollary is that if a quadrilateral is inscribed in a circle, that means the four vertices is on the circle. Then we say its opposite angles are supplementary. That means when this angle adding this angle, we'll have 180. When this angle add this angle, we got 180. Now, this actually is pretty straightforward because that's why it's called corollary based on the previous theorem. So basically what we're going to do, if we draw a line, connect this two, now you can see that this angle is half this arc. And this angle is half of this arc. Well, these two arcs makes a circle. And we know a circle is 360. Half of that, of course, 180. So that's where we, between E and G, we can do the same thing um, with the other uh, with H and F by connecting these two. Then we know the H is half of this arc and F is half of this arc. These two arcs makes a circle. Again, it's 360, half of that, 180. So this actually can be easily proved by our theorem. Okay. All right. So now we're going to do some another example. Um, Now this one is for us find x, y, z. Where's the x? Uh, find the value of x, y, z. Oh, actually, let me see. Where's x? I don't see x. In 1 second. I must miss somewhere. Okay, inscribed angle. Oh, actually, on the graph, you don't even have that. Um, huh, interesting. All right, give me 1 second. Uh, so based on this angle, x actually is uh, yeah, x actually is here. And whereas y, a, d, b. Okay, a, b, c. Okay, a, b, c. This is y. Oh, we're talking about this angle. And z is x plus 3. Z is here, this angle. Yeah, I need to change this. Okay, so x, you can see x is this angle, and the intercepted arc is here, AB. And we can see this angle is also intersect the same arc. So therefore, x will be the same as this angle, which we are given by 40. So it's 40 degrees. Okay, we find that. Now, y, we're talking about this angle, but this one actually, this two part is on the diameter. So we know this is 90 degrees. So y is 90 degrees. And z is this angle. Well, this angle, we know this whole thing here is 40 plus 30. And we know this angle plus angle should be 180. So that's 180. So therefore, it's 70 plus z, 180. So z is 110 degrees. Okay. All right. Now we're going to looking at the last theorem of this class is has to do with the tangent line and the arc. Now we're going to see that there is the four scenarios, and you can see we're talking about this angle. Now this angle we know has to be half of AB, so it's half a measure of AB. For this case, this angle is still half of AB. So half a measure AB. And then we got to this, become wider and wider, still have a measure AB. Eventually, uh, A, the B is converged with T. So therefore, what we got here is a tangent. So basically, it is the angle between the tangent and the chord. Now, as we would expect, based on the trend from here to here to here, then this angle, talking about this angle, also has to be half the measure of AB. So basically, we see that the angle formed between the tangent and the chord is half the arc that they cut, they inscribe. Good. So yeah, so basically it's the our first theorem can extend it to this extreme, have the arc. Okay, now for example, if PT is tangent to the circle, which is PT here, and AT is a chord with a chord, and this arc is 140, so therefore this angle will be half of that, half 140. So that give us 70. Good. All right, so now we're going to do some classroom exercises, okay? So the first one is explain why corollary 1 of the theorem 3-4-1 is true. That is, explain why angle A is congruent to angle 1 is congruent to angle 2. Good? Yeah, explain it, okay?
Should I type it in the chat or say it out loud?
I just say it aloud.
Okay. They both intercept the same arc.
Yeah, very good. Good job. Number 2, explain why corollary 2 is true. That is, explain why the fact that the arc x mxn is a semicircle leads to a conclusion that the angle x is right angle. So we talked about that a little bit earlier.
Um, it's sorry, let's see. The central angle is 180 degrees.
Yep. So which half of 180 give us 90. Very
Mm,
good. All right. Uh, Number 3, A. What is the sum of the measure of the red and blue arc? So we can see that based on this, we're looking for the red. One is the red line, so the red. We're talking
And they
about
both add
this
up
one.
to 360.
And the that. Good. So the red actually is, you can see red is facing X. So the red actually will be 2X. Good. And the blue is, we're looking at its intersect arc of Y. So that is 2Y. Good. Now, B, explain how part A allows you to deduce that X plus Y is 180.
Because they're both 90 and they're
Hmm? No.
because
Well, look at what X. X is half of the red.
mhm. Y is the other half.
Yeah, Y is the other half. So let's say this is the red. Y is half a blue. Good. When you add them together, X plus Y is half red and half blue. What is the sum of red and blue? These two arcs,
360.
360. Yep. And so half of that, 180. So that's how we prove that. Okay. And C, state the corollary of theorem 3-4-1 that you have just proved.
They're opposite angles of an inscribed quadrilateral
Yeah, which is what? What's the property of?
supplementary.
Yeah, so the opposite angles are supplementary. Good. All right. So now you're going to just use chat to tell me the answer, okay?
Okay.
For number 4, you can see that there is X and Y. Just find X and Y.
On which one?
Problem 4, this one. Yeah, you can also say it. It doesn't matter. Yeah, you just say it.
Oh, okay. Wouldn't it be um 100, like 130?
Oh, no. You can see that X cut the same arc as Y. So we know X equal to Y. And also cut the same arc as this, which is 38. So X equal to Y equal 38. Good.
Yes.
All right, let's do number 5.
Oh, weird. So not letting me use the chat. Would X be 130 and Y be 100?
Well, X won't be 130 because we'll see where the X is
Oh,
here.
yeah. When it
And what is the arc intersect with this arc? So then X has to be half of that arc measure, which is 50 over 2, give us 25. Good? Make sense?
Yes.
All right. Well, how do we find Y? There is a two-way to do it. One is you can see that this has to be 90 because this is the diameter. So therefore, Y, X plus Y has to be 90. We know X is 25. So Y then is 90 minus 25, which is 65. That's one way to do it. Another way is looking at this arc, this arc, this arc, this arc. Well, we know from here to here is 180, And so this arc here will be 180 minus 50, which is 130. And this angle is half of this arc. So it's 130 divided by 2, give us 65. Good. All right, let's do number 6.
Wouldn't Y be 95 and X be 70?
X will be 70, Y be 95. Very good. They add together should be 180 because the quadrilateral is inscribed on the circle. There is a name, special name for that. It's called cyclic uh, quadrilateral. Okay, number 7.
Wouldn't Y be 60 and X be 120?
No. Yeah, you're right. X is 120 because it's 60 here. Y is half of that. Yep, perfect. Good job. Number 8.
Wouldn't X be 30 and Y be 110?
No.
No.
Remember, where's Y? Y is between this line and that line.
Oh,
And so it's half this arc. Well, this arc also intercepted by this angle, which is also half this arc. So therefore, Y is 40.
mm,
Good?
yep.
So that's first one. Then what happened to the X if Y is 40?
It would it would be 20.
Huh? Well,
No, it would be 80 because it's double Y.
double Y? How do you know
Yeah.
that? Well, the to find X, you can see that what happened to this angle? This angle is facing, so we're going to looking for
Mhm.
what information we have is 150. Good.
Yeah.
So this angle then is half of that, which is what? 75, right?
Yep.
And then we know 40 plus 75, then plus X. That's a three angles, so triangle, so 180. So therefore, this is 115 plus X equal to 180. Then X will be 180 minus 115, which gave us 115, which gave us 5 here. 7 minus 1, 6. So 65. Good. All right, let's do number 9.
Um, X and Y would both be 70.
So we know X and Y should be the same, right?
Yeah.
And we know this angle should be half of 80. This was 40.
Mm.
So what we got here is 2X plus 40. That's 180. Then minus 40. So 2X is 140 and X is 70. Very good. Okay. Number 10. First of all, state the control positive. Now, here's a kind of terminology. In the if and then statement, that's basically we see or not. If this, then other is true. So we write this as if P, then Q, and sometimes we write as P to Q. And that's the original if-then statement. Now, the converse of that is the other way around, will be Q to P. And there is something called the inverse. Inverse is not P to not Q. And the control positive is basically is the inverse of this, which means is if not Q, then not P. Well, let's go back to corollary 3 and see what it looks like. Corollary 3 says that here, if a quadrilateral is inscribed in a circle, which is our P, then its opposite angles are supplementary, is Q. Okay, we got that. If P and Q, so we have to change that to if not Q, then not P. So basically it said if the opposite angles are not supplementary. So that's not Q part. Then the quadrilateral is not inscribed in a circle. Is not inscribed in a circle. So this is basically what we mean by contrapositive. Good. Okay, and so we're going to see uh, B. In quadrilateral PQRS, measure of P is 100 and measure of R is 90. Is that possible to circumscribe a circle about PQRS? And why not? Think about the uh, contrapositive we just did.
If the opposite angles aren't in a quadrilateral, no, of a quadrilateral, if they aren't supplementary, then they can't be um inscribed in a circle.
Yep, yep. Basically, that's the contrapositive we just did. Okay, uh, 11. In the diagram, angle AKB equal to angle CKD, both equal to N. So what is the measure of AB and measure of CD? So we're going to use letters, okay?
Okay,
Based on
so
the theorem.
wouldn't it be 2n?
Yeah, it will be 2N here and 2N here.
Yeah,
Pretty straightforward.
the inscribed angle theorem.
Yep. Okay. Uh, Number 12. Outline the proof of case 2 of theorem 3-4-1. Give us hint. Draw the diagram from B and apply case 1. So look at that one, case 2. How do we prove that? Here's the case 2. Yeah, the right in the middle. How do we prove this case? It told us to draw a diameter. So that's our diameter. Let's call it D. So how does that help us? Because we already proved case 1. Just look at case 1 and how do we use that to prove for case 2?
They're both equal.
Yeah, it's not equal.
O splits right down the middle.
Well, we don't know if it's right in the middle, but we are going to draw the line to help us to use the proof for case one. We proved case one, that one side is the diameter. Now we're going to prove case two. So basically, we're trying to prove that the measure of angle B, which is that, is half of the measure AC. Good. By using case one, what we the one we just proved for case one.
ABC is equal to half of the arc of AC.
Why is that? We're going to prove that. Hmm? Need help?
Yeah.
So basically, we're going to cut. You can see that if we draw like this, we cut this into two part. But based on this, now we know this side. Let's call that the measure of angle ABD. So this angle, that is half of measure AD. Well, it's based on this. We already know. And also the other side, DBC, which is the other angle, is this angle. So that is half of measure of DC. Now, if we add together, we know the measure of B is measure of ABD, then plus half measure of DBC. BC, which is, oh, not half, it's add, not half. Later on, we'll have half. And this is a half or measure of AD. Then this one is half of measure of BC. So put them together, it's half of AD plus DC. Now, AD plus DC, of course, that's AC. So that's equal to half of measure AC. So basically, we use this proof twice. So did one side of it, then we do the other side, then put them together. Good? All right, let's looking at case 3. So how do we prove case 3? So in this case, we we are trying to prove measure of B is half of measure of AC. So how do we prove that? Again, we can use what we proved for case 1. So if we draw a straight line here, we got this. It's called D. Okay, let's see how you can prove it.
Is it because the O falls outside of the angle, so CBD overlaps into ABC? CBO, sorry.
CB, there's no S. CBD is this angle. And you can see that ABD is this angle. Good. Now, what happened to the angle B? Angle B is this little bit here. Well, this one is what? Measure of B is measure of ABD minus measure of CBD, right?
Yeah.
Okay, so what's measure ABD? ABD is this one, and we know this is a half measure of AD. So based on this, minus CBD is this one, this angle, which is half of CD, half a measure of CD. Well, we can move half out, so we got measure of AD minus measure of CD. Well, AD is this part, then CD is this part. So the difference will be AC. So therefore, we got half of measure AC. Good. All right. Let's see. -1. We did that. So quadrilateral ABCD is inscribed on O. So we got triangle, equilateral. We got this. Good. A, B, C. And tangent to the circle at A, which is a tangent. And also we have a tangent at C. Then they meet at D. So they're asking, what is the figure of ABD? sorry, A, B, C, D. So we're looking for this. So different. We're
What?
asking for this. What kind of quadrilateral is that?
See what's it called? Isn't that equilateral?
Equilateral is a triangle. We already have that.
Hmm.
And we're asking for the ABCD, which is a quadrilateral. So what kind of quadrilateral is that?
Be like a kite.
Well, actually, it's not kite. Well, let's see what we have. Because this is a equilateral triangle, so we know that this arc is the same as this arc and same as this arc. So each one is 108, 120 because this angle is 60. So this is 120 here, 120 here, and 120 here. And we know this one is half of that. So that's 60. Good. Now the 60 at this, that's 120 here. Good. Now this 120 and this one is 60. 120 at 60, 180. So that means this line and this line are parallel. Now we can also know this is 60, and this will be adding 60, 120, adding 60, 180. So this line and that line are parallel. Therefore, this is a parallelogram. Good. All right. I'll see you next week. Okay.
Bye. Thank you.
Bye.